for a fifth presentation during this summer school of how I eventually found into machine learning and learned about the beauty of using it inside MIP solvers. So this is a little bit different from the presentations that I gave in the first week, in the sense that it's about 4 recent project showcases, so to say, about these topics. But first of all, I would like to start with a little introduction, getting crystal clear what I personally mean when I talk about machine learning in MIP solvers. So, and there's a couple of different terms in here. So what do I mean by a MIP? Well, the obvious, you saw that often enough by now, that we optimize a linear objective function over a set of linear constraints, some of the variables taking integral values. More specifically, in this presentation, and that's important to say in the context of ML applications, I will be exclusively covering applications for general MIP. So no specific problem classes, training a model once for a class of knapsack problems, then for a class of set partitioning problems, and so on. All that I want to look at here is extremely heterogeneous test sets like MIPLib or the internal client test sets of commercial solvers, which, as a side note, means that the existing solvers are already highly optimized towards those test sets. And as we saw in the first week, achieving like 1 to 3% improvement is considered a big win for such a test set. So what do I mean by a MIP solver? Again, the obvious part, a piece of software that solves such a general purpose MIP to proven optimality. So no pure heuristic algorithms here. And it does not require or even allow any application-specific input for the reasons that I just named. We don't consider such. More specifically, in this presentations, I will be talking about work that has been conducted in Xpress and SCIP, but similar approaches are to all likelihood implemented in other MIP solvers as well. You also see a slight variation of the flowchart that I've been using in the other presentations, because we'll be covering 2 aspects of the solving cycle here, cuts and scaling, which previous week I had hidden as part of pre-solving, but it's actually a procedure that's applied in between pre-solving, so on your pre-solved model, but before you go into your root relaxation solving. And finally, what do I mean by machine learning here? So in most of the cases, I will be focusing on learning a binary decision on which action to take inside the solver. Choose between 2 different variants of a certain algorithm. This is essentially what, in most cases, not in all 4, we'll be looking at. So you might say, okay, easy, so that's a classification that you're talking about. I will argue in a minute why I rather consider this a regression task as well. And in all cases, we'll be looking at offline supervised learning approaches. Once again, trained on general heterogeneous test sets, and we are looking for models that are easy to evaluate, ideally also easy to interpret, such that they can be run inside a solver by default. So on this question of classification versus regression, this is likely the most important learning that I had along my journey with machine learning, that in most cases, it's superior to consider regression models for these kind of classifications that I would like to do, because what's typically the label, the measure that I want to improve on, that could be something like the running time of the solvers. And while I could, of course, say, okay, this algorithm has a better runtime here, this has a better runtime here, so an A-B classification, I can put more information into this by considering improvement factors between the 2 different algorithms. So there's a better signal, more information in this. very importantly, draws are a very typical case. So it doesn't really matter which of the two algorithms you choose for various reasons. If you did a classification, you would still have to assign it to one of the two classes. I mean, there's also ways around this. But for using an improvement factorial, you just assign it a 1.0 or even more likely 1.01, 0.99. So it's not an actual draw, it's just close to a draw. And those would be the instances where misclassification in the end doesn't really matter, right? So like in this first example here, if you have an exact draw, really which of the two methods is predicted here by the model does not matter at all. So that's an improvement factor of something like 1.0. And here, that's an almost draw. So obviously, the yellow one would be the better choice. But if your model predicts the red one to be faster, still not too bad. But what really would hurt you is a misclassification on this one. And again, then classification models don't discriminate between these two cases. Okay, so far so good. Now let me take you on my journey of becoming or from being a ML skeptic to being an, well, almost ML aficionado at this point. Thorsten, don't give me that look. So that started, well, 4 years roughly ago. We were all sitting at home and had time to read to a lot of papers. A selection of ML approaches for mathematical optimization that had been published at this time, definitely incomplete, but still huge. So you would assume that some of them or many of them would have found their way into general MIP servers, but that is not the case or was not the case at the time. And you might wonder why. I mean, such a huge literature, what's going on here? And there's a couple of reasons. So one that really gets into your way is the huge variability. And even though we've spoken a lot about computational MIP solvers, we haven't really spoken about performance variability yet. So performance variability describes the phenomenon that quite often in MIP solving, if you apply small, seemingly neutral changes to a model or to the solving algorithm, which should not really change the overall behavior a lot, this is not the case. The behavior changes a lot. And you would like to get a better impression of how something is really performing on a particular model, you could, for example, apply a lot of such changes to repeat it once and try to find what's the average, the typical behavior and whatnot. But performance variability in that sense really gets into your way that there's, in many cases, much more noise than there's signal in there. This applies to outside the area of ML learning to really all the work of solver tuning that we do each and every day. So it's really hard to define something like a ground truth. Then, in many places, there are sophisticated rules already in place. Here I kind of dare to disagree with you, Andrea. You said branching is like, should be the prime candidate to apply ML. Well, if you are brave enough as Andrea, that might seem the most natural choice. So huge challenge, huge lorry if you solve the problem. I'm a bit more of a lazy person here and was looking for problems where this does not really apply, that we have the best rules. Like in branching, there's literally dozens, if not hundreds of years of person work going into figuring out good general purpose branching rules for MIP server. That's not the easiest thing to beat by any kind of new approach. Heterogeneity, mentioned now a couple of times, is an issue for learning approaches. If the structure is different for each and every input, then detecting structure might be kind of hard. And in many cases, we might not even really know good features that we could use. And one of the papers that kind of changed my mind here was your work with Julia and Pierre on the question of whether or not to linearize quadratic constraints inside a branch and bound search. I was like, okay, I see how that is working as a good application, and thought a little bit. And I was thinking hard of how I could repeat such a story, trying to come up with one place in the solver which really is in desperate need of a good rule to be applied to, and I found scaling. That's, in a sense, you can consider this as an either-or decision, because we know, exactly two rules which are pretty much covering 90% of the cases that either one of them or the other is a good incumbent rule. We know very meaningful features and no good rulers in place at that time. Okay, so to ramp up with scaling here, I would like to point to numeric stability. Again, you have seen the presentation by Ambrose last week. It's a topic where you can say a lot about, even you can write like 5 different blogs about it. And real-life applications are often very complex, very numerically challenging, much more than your typical MIP model, for example. So like 5 years ago, in my job as a FICO Xpress developer, numerical issues were a common problem where clients contacted us about. I mean, maybe not in all of these cases they contacted us specifically for this, but like about half of the client problems there, we could see how to improve the numerics, or they had genuine numeric issues. So this number has dropped significantly since then due to the work that I will present now. Pointed back to Ambrose. There's some information on numeric stability that MIP solvers can provide to you. And these can be well categorized in things that you know a priori, something like the spread of the matrix objective right-hand side. So this is a screenshot from an Xpress log here, where you would see the coefficients in your matrix. The non-zero coefficients have an absolute value. The original problem, they vary between something in the order of 10 to the minus 6 and 10 plus 2. In the scale problem, there's only like one order of magnitude between them, so that looks very nice from the numerical viewpoint. There's like 3 orders of magnitudes on the right-hand side. Still nice. Maybe the objective is a bit sketchy here, but overall, just eyeballing it, I would say, at least after pre-solving, this is not such a bad problem. There's a posteriori information. By the way, this is not from the same problem here, where the solver could report about numerical issues that it encountered during the run. And yeah, these coefficient spreads here, please keep them in mind. This is something that we will need soon. So far, I would say this information was mainly there for raising awareness of the educated user who can, well, derive some information from those numbers and statistics, maybe adopt their models or set some non-default controls to prevent issues if they observe them. Something like one more rigorous study that you could do is, and again, Ambrose has been mentioning this, looking at the condition numbers of the matrices, in particular for computing the condition number. You see you need an invertible matrix. So where do we have invertible matrices doing MIP solving one? This would be the basic matrices of your LP optima. So what one could do is compute the condition numbers of some selected or all of the LP optima that you saw, and then well, have first of all some statistics on where you classify each of those as either stable, suspicious, unstable, or ill-posed. This is completely heuristic. Well, not completely heuristic. There's actually some logic behind that, but This really says something like, I always forget the exact numbers, between or less than 10 to the minus 9 until 10 to the minus 12, 10 to the minus 15, and this is everything larger than that, something like that. And then aggregate these statistics into what's called the attention level. And the attention level is a measure which is just a weighted counting of these, or a weighted sum of these ratios. This will give you a number between 0, meaning which you would get if and only if all of your kappas, all of your condition numbers were stable, or 1 if all of them were ill-posed, and the closer you are to 1, the less likely, the more likely it is that your solver saw some numerical troubles, and that it even might give you wrong results in the end, because, well, we talked about the floating point representation of numbers. You might remember that you can represent up to 15 digits in a double floating point. The condition number tells you something about the potential error propagation. So if there's an error propagation in the order of 10 to the 15 going on, this might mean that due to cancellation, you're only looking at noise and or at numerical artifacts doing some of your computations in worst case. Doesn't mean that it has to happen, but it's kind of frightening if you see large attention levels in a problem. So finally, what is scaling? MIP scaling, well, the name is derived from scalar, so it means that you multiply the rows and the columns of your linear programming matrix by scalars. We're talking about inequality system and greater equal 0 variables that would be would be strictly positive scalars that you need to use, with the goal to reduce the overall magnitude of the non-zero coefficients in the matrix and the relative difference between them. It's a very widely used preconditioning techniques, way beyond linear programming solvers and all kinds of numeric algorithms, really. And here in our case, it would also mean that we aim for reducing the condition number of the basis matrices that we observe to reduce error propagation. Okay, so for a basic linear program, as we know it, visually, I imagine this to be something like that. So you have your coefficients that you can represent visually as the normal vectors of your constraints, and you want to bring them all on one scale. So this would be nicer than this here, in a sense. So typically, that's just close to 1. That's kind of a normalization. Mathematically, this means that you multiply all your matrix, your right-hand side, your objective function, and the domain of your variable by well, a square diagonal matrix, just that these multiplications check out. So really one factor per row and column, and we represent this as a matrix which only has entrance on the diagonal. Okay, and then the problem that you'd be solving would just use these redefinitions of matrix right-hand side objective. Good. The 2 scaling methods that I've been teasing beforehand are equilibrium scaling, which just means you divide every row by the largest coefficient. So this will bring everything to less than 1. Or less equal 1. Then you do the same for the columns. This might scale up some of the rows again, and you can potentially iterate this either until you reach a fixed point or you feel like you're done with this procedure. The other one is Curtis-Wheat scaling, which tries to minimize the least square deviation from 1 by solving this unconstrained quadratic problem here with a positive semi-definite objective. So you can use a pretty fast algorithm for computing an optimal or almost optimal solution for this minimization problem. These logarithms are binary, and also you would not use the exact scalars in the end. By the way, or same in this case, but you would round the scaling factors to powers of 2 to not get any additional numeric artifacts in your binary representation of your numbers. Okay, so let's look at a quick example. Here, application where we want to set up a home business to produce some boxes or chess pieces from wood. We want to maximize profits, have some limited amount of wood available, and there's some setup costs here. You can check for yourself that this is a valid model of this problem. This is the coefficient matrix where we've brought those binary variables that here when stating the problem we wrote as variable upper bound constraints, we brought them to the left-hand side. And you see that this is invertible, an invertible 3x3 submatrix of the constraint matrix. So this is one potential basis of the constraint matrix. And if you consider the unscaled problem for this potential basis, this would be the basis inverse. And if we do the calculation that I showed before, the condition number of this is 245. Okay. If we apply equilibrium scaling, what would that mean? Okay, we have coefficients that are larger than 1 here. So we divide by 100 both of the rows. And then we divide by the largest column factor. That's already 1. Good. So we actually reached the fixed point of that method just after one iteration. And you see that the basis inverse, because this basis, this matrix is different. This is also a different matrix, but it would lead to the same condition number. If you look at Curtis-Reed scaling, however, this is the solution that it would come with. We can actually achieve to scale the problem such that we have coefficients of ±1 everywhere. So how would we get this? Well, essentially, we can simply divide these. I'm always mixing this up. What can we do? We can divide this rows by starting from here, but then we multiply the x columns by 100, and then we have 100x plus 100x less equal 100 and divide the top row again. So that's one possible way. And this would be the inverse, and then we get a condition number of 25. So this would be assumed to be a preferred numerical behavior in many cases. It's not guaranteed that, because you're always considering sub matrices, that a single method is better for all of them, for all the basis matrix. So it's not that one fixed method is always the best. And this looked like a perfect application for a machine learning approach. The incumbent rule until that point inside the Xpress solver was use equilibrium scaling, full stop. Which is not a very sophisticated rule. So what we will do here is we try just each scaling method, the equilibrium and the Curtis-Reed scaling. This will give us information like the coefficient spreads, remember, that we saw earlier, that we derived from 2 different scaling methods. And we use them to predict which method will result in a smaller attention level, rather the factor between the 2 attention levels. So yeah, the features from the coefficient distributions are exactly the coefficient spreads massaged in a way that we divide the max by the min and apply a logarithm to this. So this would give you exactly the order of magnitude that lies between them. So if you have, well, the max is something like 10 to the minus 6, the min something like 10 to the 6, and the min is something like 10 to the 2, then this would give you 4 as the number of magnitudes that lie between them. And then use this as a feature. Okay, and not only for the coefficients of the matrix, but we also use the the coefficients of the objective and the right-hand side as features. So turned out in this study that a linear regression model was good enough to produce some very reliable predictions. We also tried some different models. They were, I mean, in the prediction quality, maybe slightly better, but we preferred in that case to have a very stable and interpretable model in the end. To give you an idea on the set of instances where we trained this on, which were particularly numerically challenging instances, the average attention level with the incumbent rule of equilibrium scaling was just a little shy of 0.12. If we had always applied Curtis rescaling, this would already have been an improvement, but it would also have led to a slowdown of the solver, which is why even so knowing that this in general needs to somewhat better numerics, this was not the incumbent rule that's being used for performance reasons. And well, the best possible, if you always made a perfect prediction for each individual model between those tools, would have been at an average attention level of 0.06, and our learned model ended up being here. So this is quite nice. So computational results. As always, don't consider only a single measure. I'm keeping a little bit the tension up here for answering Tobias' question. First of all, let's look at other measures of numeric stabilities, all the different kinds of areas decreased with using this learned model. So that's like what nine different measures of numeric stability, like the maximum conditional number, for example, that we observed here, even includes was reduced by a factor of 10. Performance-wise, the number I like to show is that this was one of the best improvements that we saw on the simplex algorithm for LPs in a couple of years. For MIP solving, it was performance neutral. So in that sense, no performance gain, but a big gain on the secondary measure, namely the numeric stability. So still very desirable. Okay. So while being on it, we continue to look at a closely related topic, only a few slides on that one, namely learning the attention level itself, not only a prediction which is the better scaling algorithm, where the prediction itself does not contain any information about the actual attention level, just which of the two algorithms would lead to a smaller one. Reminder here, attention level, a number between 0 and 1, and you want to have it as small as possible. There's a couple of negative sides of this. First of all, it's usually computed a posteriori. So after your solve, you get your information. This might have been somewhat sketchy solve that you might want to double check again. And it uses the condition numbers of LP bases, which are somewhat expensive to compute. So the most comprehensive and comprehensible numerics analysis tool that we have in the solver is deactivated by default. So the user consciously has to make the decision that they want to do this analysis on their problem. So can't we just do an ML-based prediction that says, might the current solve lead to a high attention level, warn the user about this, and then let them take a decision accordingly? So that would be an a priori prediction and should be cheap to compute using the same features as in learning to scale, which you really can directly read from your constraint matrix and have available statistics. Anyway, there was one additional feature that we used, which, well, the best way I can describe it is the conditioning of the matrix with respect to the right-hand side of the inequality system, which is cheaper to compute. What we used here was, in this case, not a linear regression model, but a regression forest. So regression, you might probably have heard of random forests. So they're a method of supervised learning, which is this subfield is also called ensemble learning because you're using many different models at the same time, which make their individual predictions, and then you're aggregating the predictions. So in the case of a forest consists of trees. So you would have something like 50 to 500 decision trees and aggregate their measures either by a majority vote or in the case of regression forest, where each of the nodes does not predict like a classification, but something like, for example, the speed up factor in our case, you would typically average them in the end. Okay, so our prediction uses a regression forest. The measure that we wanted to look at here is the accuracy of the prediction. And one way to look at this is the confusion matrix. So we defined a threshold of what we call a high attention level. Where would we want to start printing warnings to the users? And then looked how often predicted our model that it was low and it was actually low, and so on. So there's 4 different combinations. Something that I would like to point out here is the important difference between false positive and false negative errors that you have potentially heard from medicine application. It's the same, maybe not as fatal literally in optimization. So let's look at the good cases. So by far most likely case is that everything is good. So you have a low attention level for your MIP problem, and this is the number of cases where this was also the prediction made by our model. Fine. Then there's the other case, well, not very desirable from a user perspective, that you have a high attention level in the end. The case where we predicted this to be high is also like a good case, of course, for us, because this is exactly why we do this. We want to warn the user in such cases. And then there's 2 different types of errors. So there's the false positive error, which is not great. The user sees an unnecessary warning. You might scare them a little bit. They might double check and then see, no, the prediction was wrong. Everything seems to be okay. Carry on. And then there's the false negative. And this, in a sense, is the critical situation where the user might rely on you giving a warning, but you miss to give one. And the false negative rate also is in the same order of the false prediction rate of being roughly about 1.5% here. But if like these numbers, if they were flipped, you would have observed the same accuracy, but you would have a very bad predictor that classifies a lot of the actual critical cases wrongly. Okay, so how does this impact the solution process? Well, not at all. It's just essentially a model that is just there for printing a single log line here. This is what sometimes such projects can end up in. Yeah, so let's switch gears now and look at cutting planes. And in that case, the question of whether to use a local cut procedure or a global cut procedure. I will be a bit quicker here in the setup. So one example MIP, there's 2 principal algorithms that you saw a couple of times by now. One is the branch and bound algorithm. The other one is the general cutting plane method. So both are valid algorithms to solve integer programs. There's 2 principal ways to combine these 2. The one is cut and branch. So take your original IP relaxation, do rounds of cutting planes until you hit whatever your working limit was, and then afterwards conduct a branch and bound algorithm without generating cuts anymore. Or the other is branch and cut, where you keep on producing cuts during the tree search algorithm, and you might wonder which of the one is better. So should we use exclusively global cuts? You might remember the slide. So I speak about the global cut if it's generated for the global problem from the global problem at the root node and then valid by construction. Or do you want to use local cuts where you can distinguish between those that are still globally valid and those that are only locally valid? And for this application, I will focus only on the latter one. So locally valid local cuts. Is that something that you want to do during your bunch and bound research or not? That's the crucial question. Yeah, and I mean, one could easily come up with arguments for either direction. So they are a very essential part. We know from certain combinatorial optimization algorithms that branch and cut was the breakthrough procedure to solving them. There's a lot of problems which you cannot solve without local cuts, or at least not as good. But then at the same time, local cuts complicate some of the other solver features. Conflict analysis, which is the one thing that we skipped over a little bit last week, is one example of this. Yeah. Conflict analysis gets more challenging, or in some cases even prohibitive, for various reasons if you're working with local cuts. And then, of course, cutting plane generation itself just costs some time, and adding cuts to the IP makes the IP slower to solve. So you need some return of investment there for this procedure to be variable. If your local cuts don't help you with solving the problem, they would just solve down the solve. So we observed in a preliminary study that about half of the problems significantly benefit from using local cuts. A quarter of them really suffers from using local cuts, and another quarter doesn't care at all. So the idea of this project was to predict at the beginning of the tree search whether local cuts will work for the problem at hand or not. And a very glorified way of stating this question is this flowchart. And again, we used a random regression forest that we trained on thousands of customer instances, and we applied a quite conservative approach where the final decision was not made by only using an average, but also by an additional majority vote on from the trees in the forest, where I think the threshold that we ended up with was using something like 2/3 or so of the trees have to agree on one, or have to agree on switching off local cuts for us to actually do this. So the previous incumbent behavior was always generating local cuts. There's different static and semi-static and dynamic features that we use that fall into the categories that Andrea has presented earlier. So some static analysis of the problem. So row types, do you have many knapsack constraints, for examples? How many binaries do you have in your, so what percentage of the variables is binary? The density of the problem and the numeric conditioning as we saw it before. So where here the idea would be, this could be features that could tell you whether it's a combinatorial type of problem or not. These are features that try to investigate whether cutting planes might lead to more expensive AP solving or not. So what would be the impact of cutting planes on that measure? And then finally, the most important feature, the gap closed by root cuts. So obviously, this is a feature that we would expect to be closely connected to our questions. If cuts work well at the root, they might work well in the tree. The computational results in the end showed us that we could get a 2% improvement in time, 1% improvement in the primal dual integral, an increase in the number of nodes. Typically, you would say this is not, it's not preferable that two different measures kind of contradict each other, but in that particular situation, this is totally expected, because the learning procedure that you did is when would you apply a cheaper process in the tree, which would obviously, if you don't generate local cuts in the tree, there are situations where you might need to resolve things by branching, where previously you could have cut off the tree. So that's an expected behavior here. I spoke about this conservative setting, and here's a visualization when using different thresholds to get from our regression to our decision task, how this would have impacted the performance, with these two lines indicating the the two different rules of always using local cuts should be that one, never using local cuts this one, and this would like be a perfect oracle. So we got roughly like 1/3 of the way towards perfection in a sense. And then finally, very quickly, I would like to go over the last project of learning to select cuts. You learned how cuts are generated in rounds, how then at some point you have to make a selection, and why there's a trade-off and again arguments of using less or more cuts. There's some sweet spot in the middle. There's different state-of-the-art cut selection rules like the efficacy here, which is literally just the Euclidean distance between the point that you're cutting off and the cutting plane that you generated. The directed cutoff distance is again a distance measure, but not along the perpendicular line towards the cutting plane, but along the line that connects the LP solution with the incumbent solution. Again, deeper is better. There's some arguments why intuition might not always apply for these kind of measures. So two, counter examples where you could, where you can eyeball that the rules might select not the most preferable cut here. Like the, in this case here, the efficacy of the blue cut is better. The orange cut is, well, closer to the optimal solution, but this closeness only applies outside the feasible region of your polyhedron. This was kind of the motivation for considering the DCD in the end. So just from all eyeballing it again, we would probably argue that the orange cut is better because it chops off a bigger part to polyhedron. And then again, dual degeneracy might hit you hard. So consider this situation where you have two alternative optima for your linear problem. Like because your objective function is parallel to one of your constraints, or you're looking like in a higher dimension, might be tangent to one of the faces of your polyhedron. And here again, the blue part shows the blue cut shows the larger efficacy. Also could easily, if you use this, if this was the incumbent solution, the same problem would apply to the DCD. But from looking at it again, the orange cut would also cut off this node over here. So you would actually see a rise in the dual bound, which is the preferable thing to have after a round of cuts, where the blue cut just would lead to another alternative optimal solution, and you would still see your dual degeneracy here. Okay, what we used as a side part of this project was introducing some new measures which use analytic centers. The analytic center, as talked about in the presolving presentation, something like the central point of the polyhedron, something like the center of mass intuitively, either of the whole polyhedron, or if you have a dual degenerate problem of the optimal phase, and then use this as a base point for your cut selection methods. And we were wondering in which cases are these AC analytic center induced measures better, in which cases would it be our traditional measures. We used a couple of features. This time, this was implemented in SCIP and trained on the collection set of the MIP lib 2017. We did not only have two incumbent or two competing rules here, but 8 altogether. So again, we did not apply a classification model, but a multi-output regression. So we did a regression for each of the 8 measures against the virtual best of the measures. And this is one way to visualize the results. Boxen plots are an extension of box plots. So you would have the median line here in the middle and different percentiles. And by the visual deduction from this picture is that for the number of nodes here, both the median and the individual percentiles are superior to each of the individual models. So this is our, the lowest one is our learned model. And for the solver time, the picture is not as clear. Actually, it turned out that overall the geometric mean was worse for the time. So not something that ended up being employed by default here. So conclusion, key takeaways from this presentation is that modern MIP solvers by now use some fast ML models for decision making. We saw in the first half of the presentation that faster is not necessarily the only definition of better. There's also other things that you might be desirable to improve. And using regression for classification, once again, my largest learning from this project is very often a good idea in this context. Thank you.